exponents walkthrough part 2. What we're going to be covering are the powers of 10, the negative exponent rule, a review of the product of like bases rule, the quotient of like bases rule, power to a power, and product to a power. This walkthrough will give you everything you need in order to complete your homework and get an A. There's going to be a third walkthrough that will be posted after the homework deadline that will prepare you for further work that we won't get to for a little while. Okay? Alright, let's start with the powers of 10. Now, you remember from our last video that anything to the 0 power is 1. So 10 to the 0 power is 1. 10 to the first power is 10. We know that by the property of identities. 10 to the second is 100. We know just by computing it. And 10 to the third is 1,000. We also know because 10 times 10 is 100. And 10 times 100 is 1,000. So here's something really neat that I want you to note about this. 10 to the 0 is 1 followed by 0 zeros. 10 to the first is 1 followed by 1 0. 10 to the second is, you guessed it, a 1 followed by 2 zeros, and 10 to the third is 1 followed by 3 zeros. So 10 to the 11th would be a 1 followed by 11 zeros. A great way to count them up is to include these little commas here for every 3. So we can count 3, 6, 9, 10, 11 zeros after the 1. Pretty neat, right? 100 billion is the number we get for powers of 10. Powers of 10 are very important because we have a number system that is base 10. And so it's useful for expressing really large numbers or really small numbers just easily. We learned this when we did our scientific notation, and we will be using it again. So, negative exponents, a to the negative n equals 1 over a to the n is our rule. Let's give an example. 5 to the negative first is just 1 divided by 5. Let's give another example that might be kind of complex, where we have, rather than a number to the negative first, we have 1 over a number to the negative first. This is 1 over 6 to the negative first. What we have to do here is actually flip it to the top, and I'm going to show exactly why. We know that 6 to the negative first is actually 1/6, right? 1 over 6. You can know how to divide fractions, which is flip them and multiply them, and we'll get this answer 6. Now let's do something where we have a higher power. So say 2 to the negative third. 2 to the negative third would be 1 over 2 to the third. You see how our negative exponent becomes positive, it just ends up in the denominator rather than the numerator. And if we were to compute this, we would get 1/8, simply because 2 to the third is 8. This rule will actually help you immensely on the last page. Basically, 21 through 30 is a combination of applying your negative exponents rule and applying your product of like bases rule. Now for our last and final example of applying the negative exponent rule. That is one where we have a massive amount of variables. X, Y, Z, and W are our variables. The point of this is that it doesn't matter what our numbers are, they can be anything. These exponent rules will still apply. and here's how it works. All of our negative exponents will flip either from our numerator to our denominator, or from our denominator. See how this one starts in the denominator with a negative? It will end in the numerator with a positive. Let's take a look at what we did here. We have to systematically go through each of these guys. I'm going to do the numerator first, and then the 3 in the denominator. So we'll start with the leftmost numerator element, x to the negative third. This one must move because it has a negative exponent. So we're going to take it and put it in our denominator with a positive exponent. So this x to the negative third in the numerator becomes x to the third in our denominator. Here we have y squared in our numerator. It stays in our numerator because it has a positive exponent. Now we move our z to the negative first because it's negative. It becomes a z to the first over here in our denominator with a positive 1. Alrighty. Now this one, x squared. Where does it go? It stays right here in the denominator. Y to the negative first goes to our numerator because it has a positive exponent, and our w just slides over for the ride because it has a positive 1 exponent. Cool? Alright, so our next step is to apply Rule 3, our product of like bases rule, to this in order to simplify it. So we look for our like bases and we will combine them by adding our exponents. Our like bases are these two y's that are right next to each other and these two x's that are right next to each other. And it looks like this. Y cubed over x to the 5th wz. That's the answer because we can't simplify it any more than we already have. Hey, let's talk about the quotient of like bases. On your exponent properties formula sheet, this is number 4, if you're following along. So, quotient of like bases says a to the m over a to the n equals a to the m minus n. Now, I posit to you that this fourth formula is actually the combination of our second one, negative exponent, and our third one, product of like bases. And I'll show you how. First, I'm just going to tell you a to the m times a to the negative n is equal to a to the m over a to the n. I reached that conclusion by using my negative exponent rule backwards, but now I'm going to show you that they're equivalent by working it forwards. Okay? So, a to the m times a to the negative n equals a to the m times 1 over a to the n equals a to the m over a to the n. Okay, so here we see we're starting with a to the m times a to the negative n. A to the negative n we know equals 1 over a to the n because a negative exponent just puts something in our denominator. So we get a to the m times 1 over a to the n, which equals a to the m over a to the n. The thing that we are trying to prove here, a to the m over a to the n. So, since this equals this, a to the m times negative n, and our product of like bases says we can just add our exponents, we get a to the m plus negative n. Adding a negative is the same as subtracting, right? So we end up with a to the m times a to the negative n is a to the m minus n, thus proving our rule. If you don't understand this proof, that's okay. I'm going to move on to examples now. So let's say 5 to the 7th divided by 5 to the 3rd. Our formula says that this equals 5 to the 4th, right? Because 7 minus 3 is 4. And that's really all you need to know. That this is 5 to the 7 minus 3 equals 5 to the 4. But I'd like to show you the intermediary step, the step in between this and this, that proves the rule. So we're going to say that 5 to the 7th is 7 fives multiplied by each other, right? Alright, so now I want to show you this intermediary step that proves the rule. 5 to the 7th is 7 fives, 1, 2, 3, 4, 5, 6, 7 fives all multiplied by each other. 5 to the 3rd is 1, 2, 3 fives all multiplied by each other. And when we divide our numerator by our denominator, we know that we can cancel out anything in the numerator that is the same as something in the denominator. So this 5 is going to cancel out this 5. This 5 cancels out this 5. And this 5 cancels out this 5. Leaving us with our correct answer, 5 to the 4th. So now let's do an example with a bunch of complex variables. Alright, something that looks like this. Again, since this is the product of like bases, we can only apply it to like bases. This y and this y, this x and this x, and these numbers are going to combine. But we won't get any crossing there because we just can't. Okay? So, what are we going to do? We're going to say that this 3 divided by this 4 becomes 3/4. They just hang out. They stick around for the ride. We're going to say that 3/4 is 3/4. This x cubed over x squared becomes x to the 3rd, or x to the, in parentheses, 3 minus 2, right? Times x to the 3 minus 2. And then we're going to say y, so this x, here, I'll just solve it out. Okay, so our 3/4 sticks around, it's just 3/4. Our x's, we have alright, so we see that our numbers combined, 3/4 becomes 3/4, sticks around. Our x's, we have the exponent from the numerator minus the exponent from the denominator, 3 minus 2. And with our y's, we have the exponent from our numerator, -2, minus the exponent from our denominator, -5. Now I made this y intentionally complex, and here's why. I want you guys either to recognize how to add and subtract negative numbers, or realize that you should be using a calculator for these problems. So let's get our final answer. 3/4 remains 3/4. X to the 3 minus 2. 3 minus 2 is 1. So we just leave our x there. And then for our y, we have -2 minus -5. When we subtract a negative, it becomes a positive, so we have -2 plus 5, which is the same as 5 minus 2, which is 3. If you can't handle those intermediate steps that I just did, use a calculator. Even if you can, using a calculator when you're allowed to isn't a bad idea. It saves you from making sloppy arithmetic mistakes when you don't need to be making them. Cool? So, on the test, on your homework, on your quizzes, use a calculator. Use a calculator. It'll save, just use a calculator. What exponent properties have we gone over? We've gone over our zero exponent property. We've gone over our identity property, which isn't on this sheet, but I asked you to add to it. We've gone over our negative exponent property, our product of like bases property, and our quotient of like bases property. Now these three, when combined, will help you with the last 10 problems on your properties of exponents worksheet. Okay? Your middle 10 problems, that's 11 through 20, we're going to use these two properties exclusively. That's the power to a power property and the product of a power property. So I'm going to show you these two properties right now, and then you'll be able to do this entire sheet, and ideally this entire sheet as well. So let's go. Power to a power law says the power to a power law says a to the m parentheses to the n equals a to the mn, right? That parentheses is important because if you see those parentheses, it tells you that it's one of these properties from the back of your sheet, right? The other reason why this parentheses is important is because if you remember your order of operations, that's please excuse my dear Aunt Sally, aka PEMDAS, aka parentheses, exponent, multiplication, division, addition, subtraction. Alright, again, that's parentheses, these guys, exponent. I put a caret here. You can also think of it as these little numbers here. Parentheses, exponent, multiplication, division, addition, subtraction. That's the order that we compute things. So when you see a to the m to the n, that's doing a to the m, then a to the n. Why is the order of operations important? We'd get a different answer if we did m to the n and then raised a to that power, right? It would just be totally different. Let's do an example. So 2 to the third squared is, according to this rule, 2 to the sixth. Right? But I'm going to compute it. 2 to the third is 8, and then I'm going to square 8. So 2 to the third is 8. 8 squared is 64. 2 to the sixth, on the other hand, either put it into a calculator or go like this. 2, 4, 6, ooh, no. 2, 4, 8, 16, 32, 64. And I have 6 fingers out. So, that's how I know 2 to the 6 is 64. I can also just plug it into a calculator. Calculators make everything easier, especially in math. This example proves our rule. 2 to the 3 to the 2 is 2 to the 6. Let's do a few more examples, shall we? 5 to the 3rd to the 7th equals 5 to the 3 times 7 equals 5 to the 21st. Let's show it. 5 5 to the 3 to the 7 equals 5 to the 3 times 7 equals 5 to the 21st. Yes? Yes? Good? Yes, good? Okay. What if I have something that looks like this? 6 squared to the negative third. Well, a negative times a positive is a negative. 2 times 3 is 6, so I'll get 6 to the 2 times negative 3 equals 6 to the negative 6. Yes? Yes, good? Yes, good. 3 times 5 is 15 squared on this side, right? And on this side, we're going to get 3 squared is 9 times 5 squared is 25. So, on this side we have 15 squared, on this side we have 9 times 25. Cool? 15 squared is 225. Alright, so product to a power says a times b to the m power equals a to the m power times b to the m power. Let's give an example. Oh, by the way, on this formula sheet, after that it says a cannot equal 0. A can totally equal 0. I don't see why they're saying that. So let's move on. A times b to the m equals a to the m times b to the m. Even if a is 0, let me prove that for you. We're going to use it as an example. 0 times 3 to the 7th power equals 0 to the 7th power times 3 to the 7th power. Okay? Here's why. 0 times 3 is 0, and 0 to any power is 0. So, this side is 0. This side, 0 to 7 is 0, and 0 times anything is 0, so this side is also 0. It works if a is 0. Let's give a less trivial example. Let's do 3 times 5 squared. 3 times 5 squared must equal 3 squared times 5 squared, according to this rule. Let's test it. 9 times 25, the way that I multiply two-digit numbers is I do 9 times 20 is 180, plus 9 times 5 is 45, and 180 plus 45 is 225. 225 is 225, we know that's true, so this example works as well. See how I'm checking my answers? Check your answers. So let's do a complex problem where we're applying both our product to a power rule and our power to a power rule. 3 times x squared times y to the negative third times z to the negative first. All of this is going to the negative 7th power. We have 3 times x squared times y to the negative third times z to the negative first to the negative 7th. What we're going to do is distribute this negative 7. We're going to attach it to each of these guys. So we get 3 to the negative 7th, x squared to the negative 7th, y to the negative third to the negative 7th, and z to the negative first to the negative 7th. Cool? Then we're going to apply our power to a power rule to each of these three little guys where we have a power to a power. Okay? So I basically just applied my rule, and I haven't even computed it yet. I'm just saying that x squared to the negative 7th is x to the 2 times negative 7. Y to the negative third to the negative 7th is equal to y to the negative 3 times negative 7. And z to the negative first to the negative 7th is z to the negative 1 times negative 7. Now, we just compute each of these numbers, this number, this number, and this number. It's just multiplication. Use a calculator or do it in your head. I don't care. It's probably better if you use a calculator. Why? Because you'll get the right answer almost every time. Probably with more frequency than if you don't. Cool? So we end up with this. 2 times -7 is -14. -3 times -7 is 21. And -1 times -7 is 7. Now, I would be happy with this as an answer. If you put this as an answer, I'd be totally happy with it. Some people might want you to apply your negative exponent rule to move this negative exponent and this one to our denominator so that we would get y to the 21st, z to the 7th, all over 3 to the 7th, x to the 14th. We are done. That's as done as you possibly can be. This is more difficult a problem than you'll have on this sheet, and we're done with this video.